Today's topic is scalar and vector under rotation. In other words, how does a scalar change under rotation of coordinate axis? So we'll first discuss about the changes, if at all, suffered by a scalar quantity when a coordinate system comprising of coordinate axis is rotated. So let us consider a system of coordinates. This is the x-axis, this is the y-axis, and O is the origin, and z cap is denoted by a dot, or rather encircled dot, which represents that z is pointing towards the reader. It is away from the plane of the paper. So z cap is a unit vector pointing towards reader. So it is away from the plane of the paper. And this symbol is of Resnick and Halliday. Let us consider a point A and let us join OA. And therefore a vector OA is defined with respect to this coordinate system, and this vector OA has a projection of AX along x-axis and AY along y-axis. So let us write O, which is the origin, and OA is a vector under consideration. And this vector, as indicated earlier, has two parts. One is the magnitude part and the other one is the unit vector part, or the direction part. And let us write it as vector A. So this is actually scalar A and the unit vector is A hat. So A hat is along this direction. So this is vector A, which is A into A hat. Now clearly xy is one coordinate system. We can call it the unprimed coordinate system because we did not attach any prime to it. So it is an unprimed coordinate system. Now we have to rotate the coordinate axis as given in the question, and the rotation should be with respect to the z axis, which is perpendicular to x and y. Consider the set of axes shown. This is x-axis, this is y-axis, and this is the given vector A. We consider another set of axes. This is x prime, this is y prime, and let us make them coincident. So the two sets of axes, they have fallen upon each other. Now both the sets have a common axis which is called the z axis, and this is the z axis. Now with respect to the z-axis, let us give a rotation. Now this is how we rotate, and the new position has been shown. This is x prime and this is y prime. The old set of axis is x and this is y, and the angle between them is theta. Here also it is theta. Now obviously x and y make an angle 90 degrees, and x prime and y prime make 90-degree angle. The vector A is at the same position as before because we did not rotate the vector but rotated the axis. So due to rotation, the z-axis remains same. The rotation is about z-axis. X comes here, x prime, and y comes here. So the amount of rotation is obviously by this angle, which is say theta, and y also is rotated by an angle theta. So due to rotation, x goes to x prime and y goes to y prime, the amount of rotation being theta as indicated here. Now the projection of OA on x prime axis is of this amount, and say this is AX prime, and the projection of OA on y prime axis is of this amount, which let us call AY prime. Now XY are the original axis and x prime, y prime are the rotated axis. The amount of rotation being theta, or the primed axis. In coordinate representation, we can express the vector A as AX, AY in XY system, and as AX prime, AY prime in the primed system. Now the modulus of vector A, which we denote by A, is related to AX and AY in the XY system through this equation. And again the modulus A is related to AX prime, AY prime of the primed system through this equation. So this means that under rotation of coordinates, as a result of which AX, AY goes over to or switches over to AX prime, AY prime, the scalar or the magnitude or the modulus of the vector OA, that is A, remains unchanged. So this remains invariant. Invariant means unchanged or constant. So we can write scalar is invariant. This is the scalar. Under rotation of coordinates. Because there is no change in length. or magnitude or modulus. And for this reason, invariant quantities are called scalars. Let us give an example. Suppose A is 5 meters. Then AX and AY might be 3 meters and 4 meters, because (3 meter and 4 meter) can be combined to give us 5 meters. But there is another possibility also. We can also take AX prime to be 5 by 2 meters and AY prime to be 5 by 2 root 3 meters, and we can check it. And this again turns out to be 5 meters. So here we speak of a vector whose magnitude is 5 meter with respect to both frames of reference. One is the unprimed frame and the other one is the primed frame. Actually, the components AX and AY in the unprimed frame are coordinated in such a way that the magnitude of the vector is 5 meters, and in the primed frame the coordinates AX prime and AY prime are also manipulated or coordinated in such a way that the magnitude of the vector, the same vector, is also 5 meters. It should be noted that the components are not same. So we conclude that vector components are different. AX and AX prime are not same, AY and AY prime are not same, but the magnitude given rise to individually by this and this set is same. So vector components are different. They change under rotation of coordinates, rotation of coordinate system. They are different in the two frames, which are rotated by an angle, say theta. Let us now address a similar type of question on vector components. So how do the components of vector change under rotation of coordinate axis? we have already seen that vector A in this diagram can be expressed as a combination of two components ax, ay in the unprimed xy system and as a combination of ax prime, ay prime in the primed x prime, y prime system. So we can write now we'll try to express ax prime in terms of ax and ay. We'll try to express ay prime in terms of ax and ay. So this is the task which we take up now. This is the coordinate representation, and the vector representation will be in the unprimed frame in the primed frame. So this is the x-axis and this is the y-axis. Let us redraw the figure, and this is the rotated position of x, so it is x prime, and this is the rotated position of y, which is y prime. The angle of rotation is theta. Here also we have theta because the angle between x and y is 90 degrees and the angle between x prime y prime is 90 degrees. So if x is rotated to x prime by an angle theta, then y will automatically go to y prime at a angular separation theta. Now this is the vector under consideration, and let us call it vector A, and O is the origin, and this vector is denoted by vector A. Let us show the projections. So this is AX and this is AX prime. This is AY and this is AY prime. Now suppose the angle that this vector makes with x-axis is this one, and let us call it phi, and similarly the angle which A makes with x prime is, say, phi prime. So this is phi prime. So I hope the diagram is clear. Now, what is AX? AX is this distance, and AX is in fact the projection of this vector A, and therefore we can write it as A cos phi. So it is A cos phi. And what is AY? AY is the projection of A on y-axis, so it will be A sin phi. Along x it is cos, along y it is sin. Now, what is AX prime? AX prime is this distance, AX prime, which is the projection of A but now along x prime. So AX prime will be A cos of this angle, which is phi prime. So it is A cos of phi prime, and similarly AY will be A sine of phi prime. Now let us look at the figure to find out the value of phi prime, to find out the relation between the three angles phi, phi prime and theta. We note that this phi prime is in fact phi minus theta. So phi prime is phi minus theta from the diagram, and therefore we have ax prime, which is a cos phi prime. We can write it as a cos of, instead of phi prime we will write phi minus theta, and it can be opened up, so it is a cos phi cos theta plus sin phi sin theta. So we can do away with the first bracket, and we will have then a cos phi cos theta plus a sin phi sin theta. And let us now see that a cos phi is ax, so this is actually ax, and a sin phi is ay. So we have the transformation relation. Ax prime can be written as ax cos theta plus ay sin theta. Let us now look at this relation. Ay prime can be expressed as a sine of, so instead of phi prime let us put phi minus theta, and we can expand sine, and this gives us sin phi cos theta minus cos phi sin theta. And let us do away with the first bracket. We have a sin phi cos theta minus a cos phi sin theta. Now a cos phi is ax, so this is ax, this portion is ax, and a sin phi is ay, so this portion is ay, and therefore we end up with another transformation relation, ay prime which is ay cos theta minus ax sin theta. Let us write it through a rearrangement. So we will write this term first, so we have arrived at the transformation relation. So these two are the transformation relations, and if we are given the values of ax and ay, then we can find the value of ax prime as well as ay prime. So through these relations we can switch over from ax ay to ax prime ay prime. Let us pluck these relations and write it afresh. So let us, in other words, make a gist. So this sheet shows the gist. This is x-axis, this is y-axis, and it is rotated by an amount theta, as a result of which x comes to x prime, y comes to y prime. So we have two sets of axes related by a rotation of an angle theta, and the rotation is about z-axis. Z-axis doesn't change, only the position of x and y-axis changes. Now we have considered a vector a. This is the origin, this is the vector a, and this vector a has been expressed in the unprimed system, that is in the xy system, through these components ax and ay. And similarly, the same vector can be expressed in terms of ax prime and ay prime, which happen to be the components along the primed axis x prime and y prime. Now we have found out how these components are interrelated. So this is called the transformation relation. Between these components axay and ax prime ay prime, unprimed frame and the primed frame, and the switchover is from the unprimed frame to the primed frame. So from here to here, this is what we get. So if we are supplied with the values of ax and ay, using these relations we can find the values of ax prime and ay prime. Now this relation can be recast in matrix form, which is more elegant and useful also. So here we'll fill up the matrix soon, and here let us write ax ay. Now what will be here to generate this term? Here we have ax, so it is ax cos theta, so here we will have cos theta. Next, what will we have here to generate this term? It is ay, so sin theta is here, so it will be cos theta, and here we will have sin theta. What shall we write here, which is the second row first column, to generate this term? Obviously it will be minus sin theta. And in a similar way, to generate ay cos theta, we have to put here cos theta. So let us check cos theta x, this term, and then sin theta ay, this term, and again minus sin theta x, this term, and cos theta ay, we have this term. So the transformation relation has been written in a matrix representation. Now mind it, this corresponds to rotation about which axis? Rotation about z axis. Now we may be asked to derive the transformation relation with respect to rotation about x axis. Now we can do it from here by finding out how x and z are related. We know the sequence x, y, z, and then x. So this is the sequence. So rotation about z axis gives this transformation relation. Now after z comes x. Now if we are asked to find the transformation relation with respect to rotation about x axis, that means we have to shift from z to x, which again means that x will shift to y, y will shift to z, just as z has shifted to x. So the transformation relation can be easily obtained. Now let us have a try. So we are now considering rotation about x cap. So what we will do is, where we will find x we will write y, instead of y we will write z, and instead of z we will write x, and the job is done. So first the diagram. So this is the x-axis here, so it will be y-axis, this is y-axis, it will be z-axis, and the rotation is not about z but about x, so it will be x hat. Now y goes to y prime and z goes to z prime, and the angular shift is of amount theta. So the diagram is complete, and this is the vector A. Now let us focus our attention to this relation. So instead of ax prime, we shall write, after x comes y, so we'll write a y prime, and here we'll write after y comes z, so it will be a z prime. So it will be cos theta sin theta minus sin theta cos theta, and here the changes again, instead of ax we will have ay, instead of ay we will have a z. So this is the transformation relation with respect to rotation about x cap, and we can also expand and write ay prime and az prime, and it will be ay cos theta, az sin theta, and az prime will be minus ay sin theta plus az cos theta. Let us similarly try to find the transformation relation with respect to rotation about y-axis, and we will start from the result which we obtained with respect to rotation about z-axis. We note the sequence x, y, z, and then x. Now it was rotation about z axis. The task is to find rotation about y axis. Now how do we arrive at y starting from z? So after x comes y, so it is a two-step jump. So after z comes x and then comes y, so always we have to make two jumps. So after x we'll have z, after y we'll have x, and after z we'll have y. So this is the rule which we can follow. So first the diagram. Here we have x-axis and it will be z-axis. Here we have y-axis, so we'll have x-axis here, and the rotation is not with respect to z but with respect to y as given in the question. So this is the thing, and z, due to rotation about y, z goes to z prime, due to rotation x goes to x prime, and this is the vector A. Now we'll write down these relations or this transformation relation. So this transformation relation, which is the transformation relation with respect to rotation about z cap, becomes, instead of ax prime we'll write az prime, and instead of ay prime we'll write ax prime through the two step jumps. And now we'll write the same matrix, rotation matrix here. This matrix is called the rotation matrix. We'll discuss about it later. instead of ax we will have az, unprimed instead of ay we will have, after y comes z, then comes x, so it will be ax. So this is the answer. This is the transformation relation written in matrix representation with respect to rotation about y cap, and we can expand it and write az prime az cos theta plus ax sin theta So these are the transformation relations.